Welcome to the Network Laboratory. I am your lab technician, Network Prodigy, and in this lab session, you will learn how to configure a GRE tunnel between two routers. Now, in order to form a GRE tunnel between two routers, the first thing you have to take into consideration is that there has to be IP connectivity between the two routers. Now, typically, you would configure a GRE tunnel between these routers over the internet. So it means that these two routers must be able to communicate with each other over the public internet. How this is going to happen is that each router is going to have a connection to an ISP. So router 1, which is serving as a router in our branch office, he's going to connect to router 2, which is a router that is in Comcast network, Comcast being the ISP. Router 4, which is a router in our data center, it connects to router 3, which is a router in AT&T's network, which AT&T is the ISP. Now, in order to communicate on the public internet, each of these routers is going to require a public IP address. So you're going to notice on router 1, his interface connecting to router 2, which is the ISP, he has a public IP address of 12.12.12.1 configured. In router 4, on its interface going to router 3, it has a public IP configure of 34.34.34.4. So these public IPs are going to allow the routers to be able to communicate on the internet. Another thing you're going to need in order to have basic IP connectivity between these two routers is routing. Now, there's one or two ways you can do this. You can configure the routers to have default routes pointing to the ISP. So any traffic that's destined to the internet will simply just default to the ISP. Or you can configure the routers to form a BGP peering with the provider, and you simply just learn all of the routes from the ISP through BGP. Either way is fine, but in this particular lab session, we simply configure default routes on routers 1 and 4, pointing to the ISP routers. So the first thing we're going to do is just verify that router 1 can ping router 4, and then router 4 can ping router 1. Let's go to router 1. Let's ping the public IP of router 4. We see we have success. And on router 4, let's ping the public IP of router 1. And we see we have success. Next thing you're going to do once you verify you have basic IP connectivity is configure the routers for the tunnels. We're going to start on our branch office router, which is router 1. Let's come over to router 1. First thing you do is go into global configuration mode, and you have to create the tunnel interface. You simply type interface tunnel, and then you're going to give it a tunnel number. One thing to keep in mind is that the tunnel numbers are locally significant, so they do not have to match on both ends in order to form the tunnel. Even though in the real world, you will see that each router is using the same tunnel interface number, but it's not required to form the tunnel. So for router 1, I will use tunnel number 1. Once you are under the interface tunnel, you're then going to assign the tunnel an IP address. So for router 1, his tunnel IP is going to be 172.16.0.1 with a 24-bit mask. So we're going to say IP address 172.16.0.1 and a 24-bit mask. Next thing you're going to do is you have to specify what is the source interface for the tunnel. This is important because when a router sends traffic over the tunnel, it has to do a GRE encapsulation. When it does the GRE encapsulation, that involves adding a brand new IP header. And the router has to know what IP address does he put in the source IP address field of that header. Whatever interface you tell him is the source interface for the tunnel, the IP address that is assigned to that interface will be put in the source IP address field of the header. And I will show you this towards the end when we do a packet capture. So the tunnel source for this particular tunnel on router 1 is going to be his gig 00 link that connects to router 2, which is the ISP. From there, you have to tell router 1 what is the IP address of the router he's trying to form the tunnel with. To do that, you say tunnel destination, and then you put the public IP of the other router, which for router 4 is 34.34.34.34. Once we do that, we get a log message that says line protocol on interface tunnel 1 changed to up. We can verify this like we can with any other interface. We have a couple of commands. We can type show IP interface brief pipe exclude unassigned. What this command will do is it will only show you interfaces that have IP addresses configured on them. So we see we have tunnel 1. This is the IP address that is configured. It's currently in an up state. You can also do show interface tunnel 1. You can see right here, here's the IP address that is assigned, and right now the tunnel is up and line protocol is up. It also tells you what is the IP address of the tunnel source and what is the IP address of the destination. Again, that information will come into play when the router goes to do the GRE encapsulation, which I will show you at the end of the video. We're now going to do the same thing on router 4. Let's go into global configuration mode. Let's first create our tunnel interface by saying interface tunnel. And just to show you that the tunnel numbers don't have to match, I'm going to use tunnel number 4. But in the real world, you will want this to match just for best practice. Just like with router 1, we're going to configure an IP address on the tunnel interface. For router 4, it's going to be 172.16.0.4 with a 24-bit mask. One thing you're going to notice is that the IP addresses of each of the router's tunnel interface is in the same subnet. So router 1's tunnel IP is in the same subnet as router 4's tunnel IP. So it's going to be 172.16.0.4 and a 24-bit mask. We're then going to specify what the tunnel source is. This is going to be router 4's gig 00 link that connects to router 3, who is the ISP. And then we're going to specify what the tunnel destination is. This is going to be the public IP of router 1. Just like with router 1, we see that we get a log message saying line protocol on interface tunnel 4 is now up. We can verify that by typing show IP interface brief pipe exclude unassigned. We see we have tunnel 4. This is the IP address that is configured. It's currently in the up state. So now that we have the GRE tunnel configured between the routers, the way we're going to verify that the tunnel is working is we're going to see if we can ping to the other end of the tunnel. So for example, on router 1 should be able to ping the tunnel IP of router 4, and 4 should be able to ping the tunnel IP of router 1. So let's come to router 4. Let's ping the tunnel IP of router 1, and if everything is working correctly, we should get success. And we do. Let's come to router 1 and let's ping the tunnel IP of router 4. We see we get success. So that means that the tunnel is up and that each router can communicate with each other over the tunnel. What we now want to do is to configure routing so that routers 1 and 4 can communicate with each other using their loopback interfaces. So you're going to see router 1 and 4, they both have loopbacks with private IP addresses. If they try to route this traffic through routers 2 and 3, which are internet routers, if they do not tunnel the traffic, when the traffic gets to 2 or the traffic gets to 3, traffic is going to be dropped because these are internet routers and they do not know, or they're not going to know about private destinations. So they're going to drop the traffic. Or in the real world, you may see these routers configured with ACLs that's going to deny any traffic coming from or going to a private destination. So if we want routers 1 and router 4 to be able to communicate using their loopbacks, we need to configure them to send the traffic over the tunnel. One way we can do this is we can use static routing or we can use dynamic routing. What I'm going to do in this lab session is show you how to do both. Let's first come to router 1 and let's configure the loopback. Let's give him an IP address of 192.168.1.1 and a 32-bit mask. And let's do the same thing on router 4. Interface loopback 0, IP address 192.168.4.4, and a 32-bit mask. What I'm now going to do is attempt to ping router 1's loopback from my own loopback, and you're going to see that this is going to fail. Because right now we're trying to send the traffic through the internet routers, and we're not attempting to tunnel the traffic. So essentially router 4 is defaulting to 3, but since 3 does not know about router 1's loopback, it's going to fail. Or when router 1 tries to default to router 2, since 2 doesn't know about router 4's loopback, router 2 drops the traffic. What we need to do is tell router 1 if he's trying to send traffic to router 4's loopback, he needs to send it over the tunnel interface. And router 4, if he's trying to send traffic to 1's loopback, he needs to send it over the tunnel interface. Let's look at the first way to do this, which is with a static route. Let's come over to router 1. Let's go into global configuration mode. Before I do that, let me do show IP ceph for router 4's loopback. What this is going to do is show you the determination that the router has made and how he's going to forward traffic to a particular destination. So you can see this particular destination is falling back to a default route. The next hop is router 2, which is the ISP, and the outgoing interface is gig 0/0. If this traffic were getting tunneled, you would see that the outgoing interface is the tunnel. So let's fix that. Let's say IP route. We're going to put the loopback of router 4. We're going to use a 32-bit mask, and we're going to put the next hop as the IP address of router 4's tunnel IP. If we do show IP ceph again, I want you to notice that it's using the /32. The next hop is router 4's tunnel IP, and the outgoing interface is router 1's tunnel interface. This is what you want to see if you're wanting the router to tunnel the traffic and do the GRE encapsulation. Next thing we're going to do is come over to router 4. We're going to go into global configuration mode. We're going to say IP route. We're going to put the IP address of router 1's loopback. It's a 32-bit mask, and the next hop is going to be router 1's tunnel IP. We're going to type show IP ceph. We're going to put the IP address of router 1's loopback. You can see it's falling to a /32. The next hop is router 1's tunnel IP, and the outgoing interface is the tunnel. So this lets router 4 know to do the GRE encapsulation when he's trying to route traffic to this particular destination. So from router 4, we're going to try to ping router 1's loopback again, and we're going to see is it successful or not. We see we have success. Let's come over to router 1. We're going to do the same thing. We're going to ping router 4's loopback, sourcing it from our own loopback, and we see that it's working. So you got to make sure you have routing in place, and you have to make sure the routing is pointing to the tunnel. One way to do that is with a static route. The other way to do that is to configure dynamic routing over the tunnel. So let's go into global configuration mode. Let's get rid of our static routes. And now what we're going to do is we're going to configure routers 1 and 4 to become OSPF neighbors over the tunnel interfaces, and then we're going to advertise the loopbacks into OSPF. To do this, you can either go under the OSPF process or you can go under the interface level. I'm going to show you how to do both right now. Let's come to router 1. On router 1, we're going to go under the OSPF process by saying router OSPF 1, 1 being the process ID. And then we're going to enter our network statement. Now, I only want to enable OSPF on the tunnel interface. So with my network statement, I'm going to say network. I'm going to put the IP address of router 1's tunnel interface. My wildcard mask is going to be all zeros. And then we're going to say area 0, just like that. Now what I can do is type show IP OSPF interface brief. What this is going to do is show me every single interface on this router that is enabled for OSPF. And right now you can see we've enabled OSPF on the tunnel. We use process ID number 1, and it's in area 0. On router 4, we're going to do it at the interface level. You simply go under the interface. So let's say interface tunnel 4, and the command is IP OSPF. You put the process ID, whichever one you want to use. Remember, this is a locally significant number, so the routers do not have to agree on the process number. So you can use whatever process number you want. But we want the tunnel to be in area 0. You're going to see that we get a log message that's saying we have a new neighbor, 192.168.1.1, and we established this neighbor on interface tunnel 4. We can verify this by typing show IP OSPF neighbor. We see we have a neighbor 192.168.1.1. It's in the full state, and we're forming this neighbor adjacency over our tunnel interface. Let's do the same command on router 1, and you see we get the same output. Here is the router ID for the neighbor. They are in the full state. This is the IP address of the neighbor, and we formed this neighbor relationship over our tunnel interface. Next thing we have to do is enable OSPF on the loopback so that the routers can advertise their loopbacks into OSPF. What I'm going to do is go under the interface level to do this because that's what I'm more comfortable with, but you can choose whatever method you would like. Let's go to interface loopback 0, IP OSPF 1, area 0. And let's do the same thing on router 4. Interface loopback 0, IP OSPF 1, areas 0. What we should see is that the routers advertise their loopbacks in the OSPF, so now each router knows about the other router's loopback. We can verify this by typing show IP route OSPF. This is only going to show us the OSPF routes in the routing table. So you can see router 1 has one OSPF route. It's router 4's loopback. The IP address of router 4's tunnel IP is the next hop, and the outgoing interface is router 1's tunnel IP. We come over to router 4, we do the same thing, show IP route OSPF. Router 4 has one OSPF route. It's router 1's loopback. The next hop is router 1's tunnel IP, and is reachable over router 4's tunnel interface. So we go and we do our ping. We see we have success, and on router 4 we're going to do a ping to router 1's loopback, and we see we have success. What I'm now going to do is show you the packet capture so you can see the GRE encapsulation. But one other thing I want to mention is that with GRE tunnels, you need to make sure that you do not learn about the tunnel destination through the tunnel. So if we do show interface tunnel 1 or tunnel 4, since we're on router 4, the tunnel destination for this tunnel is 12.12.12.1. We should not be trying to route to this particular IP through the tunnel itself. What this will do is lead to what is known as a recursive lookup failure, and the tunnel will not work. So just to show you this, let's say IP route. Let's put router 1's public IP. Just use a 32-bit mask, and let's set the next hop to be, let's just say tunnel 0 or tunnel 1. And instead of doing that, I'll just put router 4's tunnel IP. And I'm actually on router 4, so router 1's tunnel IP. Now what you're going to see is a bunch of log messages coming, but one log message I want you to see, which is this right here: tunnel 4 temporarily disabled due to recursive routing. And that's because when the tunnel comes up, he's going to try to route through the tunnel in order to get to the destination, but you cannot do that. That's going to result in a recursive routing failure, and the tunnel is not going to come up. So if we try to do our ping again over to router 1, we see that the pings are failing. What I'm going to do is get rid of this static route. And what should happen is the tunnel should be able to reestablish, because you're not going to try to reach the destination through the tunnel. So this should allow the tunnel to come back up, which should allow our OSPF neighbor relationship to reform. And sometimes what you have to do, if it doesn't come up automatically, is go to the tunnel, shut it down, and then no shut it if it doesn't come up automatically. So you can see our OSPF neighbor relationship comes back. We can do our show IP route OSPF again. We are learning about router 1's loopback again. And if we do our ping again, we see that it's working. So just a couple of things to keep in mind. If you're trying to form a GRE tunnel between two routers, you have to have basic IP connectivity between them. if you're doing this over the internet, this means that each router needs to have a publicly reachable IP, and you need to have the routing in place to allow them to be able to communicate. And when you go and configure the tunnel, you just need to make sure that the tunnel destination is not trying to route through the tunnel. If that happens, you will have a recursive lookup failure and the tunnel will not form. Now, before we go, what I want to do is actually show you the GRE encapsulation and how all of this is able to work. So what I'm going to do is right click right here and I'm going to click Start Capture. What this should do is open a Wireshark. If it doesn't, I will open it myself. What I'm first going to do is I'm going to come to the interface tunnel on router 1 and I'm going to shut it down, because I want you to see what it looks like when it's not being tunneled versus when it is being tunneled. We're going to come back to Wireshark, and I only want to see ICMP packets. I'm going to say ping. I'm going to put router 4's loopback. I'm going to source it from my own loopback, but the repeat count is only going to be 1 because I only want to see 1 ping. And you can see it failed. If we come back over to Wireshark, here's our ICMP echo request right here. But I want you to notice there's no GRE encapsulation. So this is being sent as regular IPv4 traffic. So when router 2 gets it, he's going to try to make a decision on this IP right here, which is a private IP. But since he's an internet router, he's either not going to know about this destination or he's going to have an ACL that's blocking it. So what we need router 1 to do is to tunnel the traffic. So let's come back to router 1. Let's go to our tunnel interface. Let's bring it back up. This should cause the OSPF neighbor relationship to come back up as well. And let's do our ping again. This time we see that it is successful. What you're going to see that's different is that the ping request now, compared to the one that was sent earlier, is encapsulated inside of GRE because it's going over the tunnel. So before router 1 actually sent the traffic, he added this GRE header, and here's your brand new IP header. Here's the IP address that he's using as the source. This is the IP address of the interface that we specify as the tunnel source. So we come back over to router 1, let's do a show run interface tunnel 0, or show run interface tunnel 1. Right here we specified that the tunnel source interface was gig 00. If we do a show IP interface brief, pipe exclude unassigned, the IP address in the interface is 12.12.12.1. So that's what router 1 put as the source of this brand new IP header. We then told him that the tunnel destination was router 4's public IP. That's the IP address, that's the destination IP of the brand new layer 3 header. So as this information is being sent to router 2 is going to see that this is a public IP. He knows how to get to it and he can make the correct routing decision. This is how we're able to route traffic over the internet from router 1 to router 4. Of course, when router 4 gets the traffic, he's going to do all of the de-encapsulation. So he gets rid of this IP header. He gets rid of the GRE header. He's going to see that the IP header is destined to his loopback address. And then he's going to see that it's an ICMP echo request. That's how he's able to then respond with the reply message. And ladies and gentlemen, that is how you build a GRE tunnel between 2 routers.